Okay, in this video we are going to look at the work done by a general variable force. So first thing, let's start by looking at a force versus position graph. If we look at the force of an object that's one-dimensional, so in this case in terms of x, when we look for work, what we're really looking for is the area under this force versus distance graph's curve. So we can make small rectangular areas, but we're still going to have some either overestimation or underestimation. And we can make them smaller and smaller. What we eventually end up with is an integral. So in general, the work done by a variable force is going to equal the integral from your initial position to your final position of the force dotted with the position. In this case, that would be x. So we would have basically f dot dx or f dot dy or f dot dz. So if we wanted to do this truly in general, what we would do is we would take and look at the general integral from some initial position r, which is a vector, to some final position r, which is a vector, of the three-dimensional force F dotted with dr. So what this breaks down into being is the integral from the x initial position to the final position, force in the x direction, dx, plus the integral of y initial to y final, so on and so forth. We would even include the integral from the z initial to the z final. So in general, if we are looking at a variable force, F, such that that force has some component in the x direction, I hat, plus some component in the y direction, j hat, plus some component in the z direction, k hat. And we have a position r that's some component in the x direction, dy, j hat, dz, k hat. What we end up with for the general work function for a three-dimensional force is the integral from our initial position, our initial, to our final. These small little work sections, so those would be those small little rectangular areas that we're looking at. So it's the integral from our initial x position to the final x position, fx dx, plus y initial, y final, f in the y direction, dy, plus the integral from z initial to z final, the force in the z direction, dz. So let's look at an example of this. So let's say that we have a force that is 3x squared I hat plus 4j hat in newtons. And let's say that that is moving from coordinates 2, 3 meters to 3, 0. And again, that's in meters. So what we're going to do to find the work done in that change in motion, we're going to look at the integral from our initial positions to our final position. So let's look at the x term first. So we're going to have x initial, x final, f of x dx plus the integral of y initial, y final f of y dy. So we've got 3x squared dx, and we're going to integrate that from the initial, which is 2, to the final, which is 3, plus the integral from 3 to 0 of 4 dy. So this is going to be x cubed evaluated from 2 to 3 plus 4y evaluated from 3 to 0. So what we're going to get here, we're going to get 3 cubed minus 2 cubed plus 0 minus 12. So 3 cubed is 27, 2 cubed is 8, minus 12. So we get that the total work done is 7 joules. So that means that there is energy transferred into the particle that moved from this initial position to this final position. We've transferred energy into the system, so that means it has a positive change in kinetic energy. Okay, let's look at another example problem from your text. This is sample problem 7-9. In an epidural procedure, there's a needle that is run through various tissue layers and into a narrow region in the spinal cord. And you have to know exactly how much force to apply during the push through each layer. So what we've got here, we've got a graph of force in newtons versus distance in millimeters. And what we need to do is we need to find the work done in placing that epidural needle. Now, one thing that we could do is we can take this graph and we can break it up into standard geometric shapes. So we could have a triangle here. We could have another triangle right about here. We could move over here and make this into another triangle. We would have a small triangle here. So we'd have a big rectangle here. We would have a rectangle here. We could set this up into a triangle, a rectangle, and the question specifically asks as it is going through 30 millimeters. So we're ending right here at this point, right here. So we don't really care about this part. So here we've got 2, 4, 6, 8. So we've got 8 millimeters wide, and we're going 12 newtons tall. Here we're going 2, 4, 6, 8, 10. So 10 millimeters wide and 6 newtons tall. Here we're going 4 millimeters wide and 6 newtons tall. Here we're going 6 millimeters wide and 3 newtons tall. Here is 2 millimeters and 1 newton. This is 2, 4, 6, 8 millimeters by 6, 7, 8 newtons. This is going to be 2 millimeters by 8 newtons. This is going to be 2 millimeters by 12 newtons. This is going to be 2 millimeters by 4 newtons. So with that information in mind, we can calculate the work as the sum of all of those areas. So we have first for the triangle, let's call that triangle 1. And we'll call this 2, 3, 4, 5, 6, 7, 8, 9. So we've got 1/2 times 12 times 8 millimeters converted, so 0.008 meters. And then we're going to have, for 2, 1/2, 6 newtons by 0.004 meters. For 3, we're going to have 6 times 0.1 meter, 0.01 meter, so that's 1 centimeter. We're going to have 1/2, 3 newtons, 0.006. 5 is 1/2, 0.002 by 1. Then for the 6th region, we're going to have 8 times 0.008. For the 7th, we're going to have 1/2, 0.002 times 4 newtons. We're going to have 8 times 0.002. And then we're going to have finally 12 times 0.002. If we add all of that up, we're going to get about 0.238 joules. Now remember, I said 1 joule is about the amount of energy it takes to lift a 12-ounce soda can from your desk to your mouth. So this is about 1/4 of that energy. So we're going to leave off here for today. Next time we'll be looking at power.